months ago, I wrote a post on my newsletter around the finite volume method. If you use CFD tools, you probably come across this terminology. And to me, it's fascinating how these tools actually work. You know, how can we have a solver that can display this behavior of a fluid? When a force is acted upon it, it gives you this transient change in the fluid particles. But how does it actually work? So that's why I wrote this post, to kind of help you understand what's going on. In this video, I just wanted to clarify some of those things as we look through it together. So the biggest question, the first question I really wanted to pose to you is, what are we really solving for? You know, why do we even bother with tools like this? What are we trying to know? Well, I gave you an example of a simple square or a volume, or control volume as they're known in CFD. And these red arrows indicate some kind of force or energy that exists, is traveling into that domain. And then we have another arrow showing the exit of that energy or source. How the finite volume method works is that it deals with the law of conservation. So we're not, you know, if you go back to your school or elemental studies, we know that matter or energy can't be destroyed. It's simply conserved in reality, in nature. It's conserved and effectively accounted for in the finite volume method. We need to do something called discretize the volume we have, the area we're interested in analyzing, in computing the fluid changes in. We often resort to creating smaller parts of the larger volume we have. And we often use cells. You could have structured cells like this, or you can have hexagonal cells, tetrahedral cells, whatever type of cell shapes you're using. Ultimately, we are discretizing the volume we have. Okay, and it makes it easier for the computer or the solver to solve those individual elements rather than one large volume which we might have. It not only makes it easier, but it makes it possible. Essentially, you're creating a matrix of values that need to be solved in order to solve the whole system here. So, how does it actually work time step to time step? Well, here I've marked out a central cell in blue, and you can see the neighboring cells to that blue one are all in green. This is to show you that in principle, what happens in the finite volume method is that we are, at any one moment in time, in each time step, we are checking a single cell, and we are checking the neighboring cell values of the field. So this might be the velocity field, this might be density, temperature, whatever you're looking at. Essentially, you are evaluating in each time step what the values are of the neighboring cells and the central or the currently checked cell. Let's take an example. The blue cell might be 0.2 and the neighboring cell might be 1.2. You can see that we have a gradient in the values here, and the gradient drives the change that occurs in the blue cell. So at time t, we have these values. When we step forward in time, this is t plus 1, we are evaluating those values. And now the blue value becomes 0.3 and the green value or green cell becomes 1.1. This increase in the blue value and the decrease in the green value essentially shows that the flux or the gradient is driving the blue value up and the green value down. And we use this essentially in each time step over and over again, the same equation in a loop. So essentially we are trying to find the equilibrium state in the values. OpenFOAM specifically is open source. You can check the finite volume time stepping schemes it has, and it actually has a file if you've ever used OpenFOAM called FV schemes under the system folder. And here you can define which type of time stepping scheme you want to use. There's one, for example, called the upwind scheme, and that uses the cell values upstream of the cell you're checking. There's the central time stepping scheme, which uses the average of two neighboring cells, thereby giving you a more accurate account of the values that it's finding. And here I did provide you with a code straight from the SimpleFOAM solver to indicate how OpenFOAM actually does this. And you can see time step used here, the DDT, referring to the time step in the equation. And then you have the velocity component being incremented, changed, yes, and then subtracting the diffusion element or component from that to give you the change that occurs in that particular cell. This is happening over and over and over again in a full loop, and that's how you get these fluctuations in velocity that we're seeing here, for example. And that's fascinating to me. You know, now as a developer of tools like this myself, you know, it's a real privilege to create tools that allow for this kind of insight for engineers and researchers. You know, it's absolutely fascinating to work on that end as well. In the description below, you'll find the link to my newsletter, where I write weekly, to try and help you understand simulation tools and solvers. And you'll also find a link to this post, of course, where you can read it in all of its detail. Thank you for watching, and if you like the video, hit the thumbs up. If you want to see more like this, subscribe to my channel, where I will try and post regularly. So thank you very much for watching, and I'll see you in the next one.